In this presentation, I will describe the process used to produce X-rays. If you are unfamiliar with the anatomy of the X-ray tube, you might want to review my X-ray tube lesson before you proceed. This process of X-ray production is common to all X-ray machines and CT scanners, regardless of their use or manufacture. Before we begin, I want to clear up a common misconception. X-rays and X-ray tubes have nothing to do with radioactivity. Additionally, patients exposed to X-rays will not become radioactive after the examination. Radioactivity occurs when unstable atomic nuclei strive to become stable. Radioactivity cannot be controlled in a manner similar to X-ray production. On the other hand, X-rays and X-ray production occurs outside the nucleus and can be controlled with great precision. Some generators are capable of exposure times as small as 1/1000th of a second. In addition to controlling the time of exposure, the radiographer can also control the amount of radiation and that radiation's energy for any technique. This is accomplished by regulating the rate of electron flow across the tube, measured in milliamperes, along with limiting the exposure time. Milliamperes multiplied by the exposure time yield a number called the milliampere second, which indicates the total amount of radiation used in the exposure. Finally, the penetrating power of the X-ray beam is also under the control of the radiographer by setting the kilovoltage level for any given exposure. The range of kilovoltages for modern X-ray machines vary from 40 to 130 kilovolts. To begin the process of producing X-rays, the filament, a thin coil of tungsten wire, is heated until white hot. As the filament heats, electrons boil off its surface and form an electron cloud around the filament, called thermionic emission, which translates to producing electrons using heat. In the next step, a high voltage charge from 40 to 130 kilovolts is applied to the anode. This will cause the electrons, loosened up by the hot cathode, to accelerate toward the anode. At this point, the electrons will move from the cathode to the anode. As the electrons accelerate, they gain energy, enough energy to produce X-rays. When decelerated, the electrons are traveling at a fraction of the speed of light. When the electrons arrive at the target, they interact with the atoms in the target and rapidly decelerate. When matter decelerates, it loses energy. This energy is given off as heat and X-rays. 98% of the electron energy is given off as heat and 2% as X-rays. A small percentage of the X-rays are allowed to escape the tube via the tube port and are shaped by the collimator before interacting with your patient's tissues. Let's take a minute to review the sequence of events that leads to production of X-ray beam. First, heat the filament to white hot. This produces an electron cloud around the filament. The higher the MA station selected, the hotter the filament, the larger the electron cloud. This process is called thermionic emission. A high voltage charge is applied to the anode, and this accelerates the electrons from the cathode to the anode. As the electrons accelerate, they gain kinetic energy. The high energy interact with the atoms in the target and are decelerated. When the electrons decelerate, they lose their energy in the form of heat and X-rays. This will end my presentation. Thank you for your attention.